Now we're going to look at a key concept of modern cryptography, or maybe even the key concept of cryptography, the one-time pad. To introduce the one-time pad, I first have to talk a little bit about the fundamentals. So, you are hopefully familiar with the XOR operation, the exclusive OR. I included the truth table here. And exclusive OR output is then true if two bits are different from each other, and otherwise it's false. So why does that matter? Well, let's make an experiment. I've implemented XOR on arbitrary byte strings in Python here. It's the XOR implementation. And then I use it here. So I XORed the byte string hello with ABCDE. And what I get out of it is this weird looking byte string that looks nothing like hello and nothing like ABCDE. And if I XOR this byte string that comes out of this XOR operation with ABCDE, so the same byte string we used here, I actually get the original message, the hello, back. So it seems like we can use XOR for symmetric cryptography purposes, since we can look at this ABCDE as the key and hello as the message. And in between, after the encryption, we have this gibberish, and after this decryption with the same key, we have the message again. That's because of one property that is commonly used of XOR. If I XOR something with itself, it vanishes. Because one thing, XOR itself is 0, and everything XOR 0 is itself. So if I XOR something with 0, it's a no operation. Okay, so it looks like we can use XOR for encrypting and decrypting in symmetric cryptography, but is that a good idea? Is that secure? Well, here's one very fundamental sentence in cryptography, and that is, if we have a random variable over a bit string and another random variable that's independent and uniform, also over bits of the same length, then the XOR of both random variables, let's say, is also a uniform random variable over the bit strings of this length. So this might sound very abstract and not very useful, but it's actually extremely useful and an extremely important concept. So if I have a message, as you see now, if a message hello has a byte string, and I XOR this message with a truly random key. Use this as a variable here, and this key here is truly random. So here it's uniform distributed and independent. That means it's truly random. What we get out of it is a ciphertext that is also uniformly distributed. Even if our message was not uniform at all, XORing it with a uniformly distributed key makes our ciphertext uniformly distributed. And why is that important? Well, on a high level, if our ciphertext is uniformly distributed, that means every bit is equally likely to occur, then it leaks absolutely no information about the underlying message, because getting the original message out of something that's perfectly random is impossible, which is why this encryption is perfectly secure if the key is actually truly random and the same length as the message. Okay, this is what's called the one-time pad. So imagine we implement the one-time pad. We say, okay, we get a key, we generate a truly random key, so uniformly distributed and truly random. What that means, truly random, we'll see in a later lecture when we talk about entropy. Now just imagine we have this truly random key. We XOR it at our message that we want to encrypt. So we have this message we attack at dawn. We encrypt it with our truly random key using the one-time pad, and then get the ciphertext out of it. And as I've said, this ciphertext leaks absolutely no information about the underlying message. And why again doesn't it leak any information? Well, let's look at it from another perspective. Imagine somebody gets this ciphertext, and then from another source he gets, okay, here is the leaked key, and it uses this leaked key. Somebody told the attacker, okay, this key is the actual real key, and he XORs this, oops, there's a place missing. He XORs this leaked key that he thinks is the actual key with the ciphertext and gets a message out. And the message is, we do not attack. Well, of course, in XOR we can input any key we want and therefore fabricate every message we want. And since our ciphertext is uniformly distributed, every message, every outputted message that is possible is equally likely. So it is that the original encrypted message has this content is as likely as that it has this content, just looking at the ciphertext. So every message and therefore every key is equally likely. So taking this further, we could also use another key. Okay, now we say this key is the actual key. Give this to the attacker uses this key and gets another message. So every key, every message is equally likely, and therefore the ciphertext does not leak absolutely any information about the true message. And it doesn't matter which key we use, we'll always get out a message that is as likely as all other messages. This is called the one-time pad, and it's the only, from a theoretical perspective, the only perfect cipher. So, problem solved, we have solved cryptography. Well, no. Why don't we use that? Well, first, the key has to be perfectly random, and it has to be as long as the message itself for this cipher to be perfectly secure. And when you think about it, that doesn't help us much in reality, because we then have a key that's as long as our message, and we somehow have to transfer this key over our insecure channel to our communication partner, so he can use this key. And if we have the possibility to transfer a key that is as long as the message and can never be repeated, well, then we might as well transfer the message itself, not the key. So in reality, this one-time pad, it's called one-time pad because we can use a key only once. If we use it multiple times for different messages, it becomes insecure. It's called the many times pad. Well, why do we even still talk about it? Well, it's the perfect cipher, and it's the only perfect cipher, and a lot of things we do in symmetric cryptography actually try to approximate this security and try to bring this one-time pad idea into reality.